Hello, hello, am I audible? Okay, okay, okay. I'll check the recording. Okay, I think the recording is going on. Yeah, slides is visible. What about slides? Okay. Do you have any doubt from the last class and or the previous last years? Any questions? You don't have any doubts in the last class? Okay, then we'll continue. Huh? After 17, we'll continue. Don't. So whatever slides I have, then among them, that definitely we'll finish that within 2 hours. Actually, what we did, what I told in the last class, last two class, that's mostly that based on our oxidizing agent and their applications and how just you will use different kind of oxidizing agent with when then you have two or three different functional group and how you will oxidize selectively only one and sometimes also that we discuss some problem related about the relay oxidation, how that it will from alkene to how you will synthesize alcohol, or if you have any that keto and the ineligible keto, in that cases you will get a corresponding diketone, how it synthesize and their mechanism also. Okay, we'll start. You don't know what that they will see the lectures. That's if anyone is new to the this class, anyone is new or that's who know me or they already. Guys, anyone is that's the new student any they have joined or that you know already. No one is known now. Okay. Yeah, this is our week three, the lecture. And in this lecture, we'll discuss generally some problems related about the particularly the reduction based reagents, that how you will do that the reduce that the different kinds of functional group, that even also sometimes that's most of the time that we have focused on that the carbonyl functional group, and also this the radioselectivity and stereoselectivity, how they will select. And in some cases also we got some mixture of products like that mixture of products that from with the stereoselectivity from that wedge position or that the dash positions, that and how we'll control that by the different kind of reducing agent, how we'll selectively the synthesis one that the diastereomer as compared to the other diastereomers. We won't see about the anything like anything about the enhancer selectivity, but most of the time we'll send that checks about in reaction the diastereomer selectivity. The diastereomer selectivity in any reaction is that the most the important things. The how we will control the diastereomer selectivity by using different kinds of reagents with your the reaction partner and to get that the more selectivity. That's why nowadays that what people do with that with that the discovery of that the different type of reactions. That's why catalysis is that the most important thing in that synthetic organic chemistry nowadays. The catalysis, because from that the catalysis only that we can control most of that the regio and stereoselectivity. If you don't use any that the catalyst, that the like you call them as any type of metal catalyst or any other type of catalyst, then there is chances that you will get the different kinds of products. Even you will get that the same kind of product, but you will get that their diastereomer ratio is very different. Like that you will get very poor diastereomer ratio, like that the 4 is to 1, that one diastereomer will form as a 4, that the 4 and other that the other diastereomer that will form as a 1. The ratio also most of the time the diastereomer selectivity may that the in all cases it should be like the more than 20%, sorry, more than 20 is to the 1 DR, we call them as the single DR. That's a single diastereomer. More than 20 is to 1 DR. Call them as a single DR. Okay, that's in lecture I will tell you. That all. Yeah, again I am asking that whether my voice is clear now and the slides is visible. Okay. Yeah, this is our first question that we have the cyclic alpha beta unsaturated ketone, and we are using that sodium borohydrate, that's in methanol solvent, and 0 degree Celsius. We just take that 0 degree Celsius, that's the most important things. Then in the most, what happened? Really? Yeah, now it's okay or not? Okay. What about now? Now it's okay now? Yeah, what will happen in these cases? That we have that sodium borohydrate. Maybe you know about that sodium borohydrate. Maybe that the little about the sodium borohydrates, that what will happen that in presence of, and what is the we call it what kind of reagent is that sodium borohydrate? Yeah, reducing agent. That generally it will reduce that which kind of functional group? Yes, most of the time it will. Yeah, yeah, it's good. But in these cases, what will happen? The you see that we have two different type of conditions by using sodium borohydrate. Okay, before answering the question that in that every kind of that sodium borohydrate reductions, please guys unmute. Huh? Guys, please on mute. I want to say. That in every kind of that the borohydrates, that reduction cases that we are using, you will see that the always we are using the solvent is methanol. Methanol. Okay, that's the methanol solvent. Here, this is MEOH is nothing but methanol. Why that we are using that the methanol solvent? Why not that the, any other solvent like dichloromethane, DCM, or that tetrahydrofuran, or diethyl ether, or that toluene, or mesitylene? These are also solvent. Yes, yeah, polar protic solvent is needed for this kind of reactions. Okay, then you just predict that the which products will get in that the both cases. What will be the other products that B? Yeah, I think B that you can answer. B so is A. What happened? What you will get here products. The the product will get, yeah. Okay. It's not hydroxy, it's the alcohol. Okay. Ha, ha. But in presence of that sodium borohydride only, that in presence of only sodium borohydride. With the in B cases that will get which product? Only ketones. Anyone? Anyone else? Yeah, I'm not seeing that the which answering because that in presentation mode that I'm not seeing that which answering it's for everyone. If you have any that if you know something, then you can unmute and answer. I'm not seeing anyone that you will answer wrong things. That doesn't matter. Okay. Yes. Yeah. That's one. Yeah. That's yeah, the product of A is that's correct. But what about that B? But after that, the one for addition, if there is any, that any that whether the keto will be that will get that keto or that the further reduction will be happening. You don't think that the further reduction will won't be happen? Yeah. In that cases, we'll get the OH. That is the most important thing. Okay. And not inulate. Yeah. I'll show the mechanism. Do you know that the how to perform that sodium borohydride reductions in lab or in that the practically how we will perform the sodium borohydride the reduction reaction? Huh? That's in normal that you will take that the normal methanol, then you will get the 100%. Whether you think that you that if you use that the whatever that methanol that you are using from that the reagent that you will get from any that the chemical source, then you will use that methanol, then you will get that the more yield. You think, or if you put the reaction in that the air atmosphere, then you will get more yield. Yeah, that from nitrogen atmosphere that you will get that the good yield. And why that we are using? Then how you will add that sodium borohydride that you will add in that the directly, and how you will add. Yeah, why that the portion wise? Yeah, yeah, that is only reason that we should add in 0 degree Celsius also. The portion wise that we should add the sodium borohydride. Okay, okay, that's the good thing that you should know. But how will put that the sodium chlorides one? That sodium borohydride is that somewhat that is stable in that the we call them as air atmosphere. Somewhat, it's not completely, but somewhat it is stable. But sodium chloride, that the trichloride, it is that the much more that we call them as the moisture sensitive. chemical. For that, we have to be very careful to put the reactions. People are still joining. Okay. Hmm. Lecture on chemistry is there, guys. Yeah, guys, you can unmute. Lecture in chemistry, which that's you just please mute. Sorry. Yeah, what actually happened in the cases? Yeah, this is the things that I have got from it that from a previous paper, but this is not actually true. That's whatever that's in books it is written like that, but it's not actually true. That's whatever that we are using. Guys, please unmute. Sorry, mute. I think I yeah, lecture in chemistry, please. Okay, I can remove it. Yeah, first I will tell them if they want that listen, then definitely I will remove. Yeah, actually, what will happen generally in this case? This is that the results I got from a books, but this is not actually true. That's when you will use that sodium borohydride. If your reaction is completed, that the almost completed, then only selectively you will get the alcohol. That secondary alcohol you will get. If your reaction there is some still, if the reaction is not completed, and before that you stop the reaction, then you will get all that products. But those people they have that reported this method, they completed that reaction, and whatever their the intermediate products they got, they have after that also their intermediate we call it the product also react, and they at last they got that they have reported 100%, but generally people they don't get that the 100% because that in workup also that you will lost something that in when you will do the column chromatography, that the purification method, in that method also that we lost something that if you put the reaction in very high scale, then we can say that the our yield is that the greater than 99%. But the people whatever reported that I am showing, but in that when you will put the reaction in generally in your own that you will put, then you will get that the whatever the product, maybe you will get that the some ketone product also you will get, and that your alcohol secondary alcohol that you will get that the more than 90%, that's I can confirm that, but you will get there is some ketone product also, and this alcohol that water, the alcohol and ketone, these are volatile alcohol. Okay, so that when you will put the reaction in your lab, then that you should be careful that when you will evaporate the solvent, you should be careful that what is the yeah, what is the temperature of your that reaction sorry, that the water bath in the rotary evaporating, that you should be careful about that whether your compound is volatile or not. This thing you should know. Yeah, what actually happened that the borohydrates that BH4 minus, that these are the we call them as hydrate donors. These are, and these hydrate donors, yeah, first it will attach to our the alpha beta unsaturated carbonyl group, that terminal carbonyl group. As a result, that it will form that the corresponding enzyme. Why that the protein solvent is needed? Because in that the intermediate that we need proton. That's why in all type of that sodium borohydride reduction cases we need the protein solvent. The inhalation will be happen, and further the whatever that if you use that more equivalent, then you will get your corresponding the alcohol to reduction to that the 1 2 addition will be take place, and we will get our that the alcohol product as a selectively that we will get our alcohol. But why that we won't get that the in presence of cerium trichloride? The reason is what? Yeah, this is it, that the you see that the we'll get some product of that the alcohol also. So we won't get the keto, but we will get the some product of alcohol, and selectively the allyl alcohol we get as a 97% heat. These are the reported one. That I'm not putting the reaction, but these are the reported from that our literature survey. In journal paper they have published and they have reported they got as a 3% of alcohol and that 97% of that allylic alcohol, and they won't get anything about that cyclopentanol. So that you are saying that this is a hmm, yeah, actually what happens that if you have sodium trichlorides and sodium borohydride, first they will react. They will react and then it will form that the sodium trichloride hydrate, and that hydrates this one, the sodium that will bind to our the keto one. Ketone because this is a Lewis acid. Thus Lewis acid it will be bind we call them a coordinate to our the carbonyl oxygen group. As a result, there in that cases our hydrate air will be transferred easily to our carbonyl group as compared to our the alpha beta unsaturated the whatever the ketone will be there. Sorry, that the alkene terminal one that it will easily attack to our the carbonyl as compared to our we call them as double one. That the alpha beta unsaturated ketone double one is there. That's why in this cases particularly we reduce our keto groups that in places of double one. But you will get that some that amount of our that is the secondary alcohol also. It is not that you will completely got that's your product as a allylic alcohol or that secondary alcohol. So, guys, wait, someone is joining. Okay, in that the first cases that when the product will be B, in that cases uh, as there is no Lewis acid, that's why we got only the products of that the secondary alcohol. That it will completely that reduce to their corresponding that secondary alcohol. Here this is alcohol, but when we have that the any Lewis acid like particularly sodium we call it trichloride. In those cases, that it will form a that serum dichloride hydrate, and this hydrate these are the hydrates, and we call them as the hydrate Lewis acid reagent. These are the HCCl2. These are hydrate Lewis acid reagent, and they can transport their hydrate to that the ketone, and we will get our corresponding the alcohol product. Okay, breaking. Okay, yeah. Now it's okay. To check maybe your internet or maybe that the my internet is good or not. If it is fine with everyone or with that guy only. If it is okay, my voice is okay or now okay na? Yeah, we'll go to our next let's yeah. Do you know about that the birth reductions? Birth reduction, you know? Yeah. Ah, yeah. In this cases also, in this reaction that we need a protein solvent, the general ethanol that we are using in this case. But in laboratory, it is very difficult to put that the birth reductions. Do you know why? Do you know why that say it is what? We are using that the sodium metal that we will use, but the most that difficult things in this reaction is that the liquid the ammonia. That whatever the liquid ammonia that you are using, that you have to be condensed. That by using that the liquid nitrogen, the condensation process is needed because that our liquid ammonia that if you put in that room temperature that if you put the reaction in that the room temperature that the minus 70 degrees Celsius, then definitely that it will evaporate. So to condense that we are using liquid nitrogen, and you have to put yeah, this is a setup that we have. In that setup that you can condense that the liquid nitrogen and sorry that the liquid ammonia, and that ammonia goes to your reaction mixture and you will put the reaction. This is a very difficult kind of a reaction, the Botts reaction. But that's okay. But what will be the product we'll get in this case? And you should that tell the dash selectivity also. That the which That which isomer we will get as a major product. What? Not changing. Yeah, I moved to already, but I don't know. But now it's okay. Okay, that's one. Now it's okay. Ah, ah. Then we'll get that the which product we'll expect. The product I'm showing is that the definitely it will reduce to our ketone to our corresponding alcohol. So we'll get secondary alcohol. But which product will get selectively? Both will get. But which product will be that the major product? Why? That- Why? Is there any reasons that yeah? Do you know that the what is that in cyclohexanone system that yes. Do you know that the mechanism of that the Birch reduction? That how the mechanism of that Birch reduction will is that it will go to how it will convert from that ketone to their corresponding ketone. The mechanism you know that you can't say that suppose that if you have a if that methyl group that is in three position if it is not in say that the two position then you will get that the trans one always. Yeah, these are that is, you remember do you know that the, what is the region actually. Yeah, you say that the steric hindrance, but okay, okay. From that, the chair conformation, you can say that which one will get the major plot. Okay, but whatever you are saying, that is that the correct answer that you will get the trans product. But in that the most of the cases, because that in cyclohexanol system, that if it is that the trans, one or two positions, if they are trans, in that the different that they are the we call them as the stereochemistry, then we will get in chair conformation they has to be in a that the equatorial position both one. That's why these are more we call them thermodynamically stable products. Or yes, in these cases you won't get any hydrates. The mechanism is generally actually what will happen. Yeah, radical mechanism will get that whatever our sodium metal. Sodium metal is free. The sodium metal they have free electron. That's why that it donate that the free electron to that the ketone, and that's why it will reduce. First, we'll see. Uh, First, we'll draw that the most stable conformation of our ketone. Okay. Yes. Any problem? What will happen? First, you just draw your most stable conformation of cyclohexanone, well, and after when you sodium that it will donate the electron and first it will it reacts with our carbonyl group and we'll get a radical that the radical anion. You should this see that this is a radical and the orbital I have shown here is that a radical ion. That we in that the orbital we have only a single dot. That's why it's a radical. Radical carbanion first it will form. After that we are using the protein solvent. Then it will abstract that proton and you will get first it will form to their corresponding OH. But in this case, the the radical attack that it should be from that the equatorial to get that your product to that the thermodynamically favorable product. That's why the attack it should be from that the axial, and you will get your OH group, and whatever that the O minus group, it should be in equatorial. That is the only reason that we got that the trans product. Sorry, in this case, that whatever that methyl, that will be in that the 4 position. Okay. Yeah, this is the mistake from mine. I'm not checking. Guys, okay, okay. Huh. That's the thing. That whatever the methyl group, that will be, you think now it that that will be in that the 4 positions also. Okay, that you can put in that the second position also. Whatever that methyl groups, yeah, I will draw otherwise. Let you know. Yes, yes, yes. From where that you can put that the cyclohexane that your ketone will be in that the in every position also you can put. But for most that for to understandable that we can put in that the in a that top one, that to know that the facial selectivity, that you can put in that the every carbon also, that whatever the six carbon in that, first you can draw the keto in that which form. But for better understanding, that we can put in that the top, that the right top or that the left top, that we can put. It is not like that the that you have to put in that the only particular that carbon in that the why not in that the other carbon. It is not for, but for better understanding, the best view is that you can put in top. Huh, first that when you will draw, suppose that you have a, suppose this methyl group, that will be in that the four positions. Okay. Then suppose that if your methyl group that you will put in the axial, then you will get that the less stability that as compared to your methyl group that is will be in that the equatorial positions. Okay. Huh. Yeah. First that you have to draw that the most stable conformation. It's not the, okay. Still any doubts? Okay. Then we'll get radical anion, and from the radical anion first it will form, sorry, that first carbocation, sorry, the radical is there, again sodium metal, that it will donate the another electron, and we will get that the carbanion. This is the lone pair is said, but we have that orbital, that's why we call them as the carbanion. And that carbanion again after the proton from ethanol, and we will get our hydrogen from that the axial position. That's why in almost all cases we got that the thermodynamically favorable product. Almost all cases in Birch reduction we got that we'll get definitely that the thermodynamically most favorable product in all cases. There is some exception, these are the, but most of the cases greater than 99% will get thermodynamically favorable product because of that this radical anions that the sorry, that the carbanion that will be formed, that is that the most stable carbanion that will be formed. That's why it will always give their most stable thermodynamic product. The carbanion that the intermediate, what the carbanion that will form in that the reaction mixture, that will be the most stable carbanion. That's why we'll get our products as a more thermodynamically favorable product. Suppose that's intermediate is not stable. Suppose that's if that, suppose you have a reaction, and you have a that the like a carbocation or the carbanion or radical, but you get a get an that the intermediate, and that intermediate is not stable, generally stable, then you will get in on that cases you will get your major product as a kinetically favorable product. But when your the intermediate is stable, in that cases you will get your most stable product as a thermodynamically favorable product. Okay, in this case, and in this cases particularly that we will get as a ratio. You see, this is the ratio that if you use the different kind of that reducing agent to that keto, that if you use That's the sodium alcohol that you will get as a that exclusively that you will get thermodynamic stable as a the ratio of 99 is to 1. But if you use that lithium aluminum hydride in this cases you will get major product as a this one you will get major product, but the ratio you see the ratio is 18 or that we call them as the 82. But when you will use that sodium borohydride, that you will get 70 or 31. And when you will use that the aluminum, that the trash hypopropoxide, in that cases you will get that 42 and 52. That is exclusively that both product you will get. And when you will use that the hydrogen and that the carbon charcoal also for hydrogenation reaction, in that cases you will get that 30, and that the other product you will get as a much more we call them as a selective product, that is the 70%. Okay, that's why that the sodium liquid ammonia we call them as the birth reduction, it will only gives or that the more thermodynamically stable as a ratio of that the 99 is to 1. That's why to choose any kind of reducing agent or sometime also that the oxidizing agent or that any kind of reagent that will be particularly gives it will gives that only one kind of product. That is that the most important. In this case, this diastereomer will be major product as compared to the other diastereomers. You know that the what is that the meaning of diastereomers? Maybe you should know. Yes. Then the yeah. What is the difference between enantiomer and diastereomers? These are that the how to identify the enantiomer and that we call them as diastereomer. That the definition you are saying that the how to identify that enantiomer and diastereomers. But what is that the particular that the chemical that properties? Yes. Yes. Yeah, in case column chromatography, that's it is not always possible. So sometimes they are we call them as separable diastereomer. In that cases, that you can separate, but most of the cases you can't separate that the diastereomers. Because you can that separate somewhat, but you can't separate that completely in column chromatography. In some cases you can that if it is a we call it, but to separate, and there is another process also that we call them as the recrystallization process. The recrystallization process also that we can say resolution is that's the different process. In the resolution that you can resolute a particular diastereomers or that the particular enantiomers also. Both that you can resolute. Enantiomer also you can resolute or diastereomers also that you can resolute. It's not a problem. But generally how to that you can distinguish that the two enantiomer, that how will you find out that suppose that is in a reaction mixture that you have a enantiomer and that and their ratio is something like that one is above and sorry the one is more and another is less, then how you that you will find out that the which one is more and who that which one is less. Do you know that okay, yeah, that's meaning that the you know about that HPLC. Do you have any about the that the what? Yeah, yeah, that's I understand. But do you know that the how to separate that any that the racemic mixture or chiral compound in a HPLC? HPLC that we have to be separate. In that resolution we can separate. That's okay. But how we'll check? Suppose that you don't want to, you don't need to that say resolute that you want to see that. Suppose that you will put a reaction trial reaction and that we are trying to synthesize a compound. That compound is a chiral compound. Suppose yeah, and you want to check that the how much amount of that the one isomer will be formed as compared to the other isomers. First you have to check. Then only you will separate. Yeah, that enantiomeric excess. Then how you will check that the enantiomeric excess? Do you know from HPLC will check Do you know that the mechanism of HPLC? Anything? The asymmetric versions? Anyone? Anyone has? No, no. That's a. This one is a we call them a top question, but as you are working in asymmetric synthesis, that's why I'm asking. Anyone? Do you know that's the no that enzyme? These are the different things. Generally, in that when we will try to because they separate any that the reaction mixture that when we will try to suppose that for any column chromatography that we if you have that the two or three different compound and you want to separate two that we call it the one compound for that you do column chromatography, but when you have two or three different kind of enantiomers or that diastereomers also that's if you have two chiral center that you will get that the four kind of that molecule in your reaction mixture. For that you need the chiral column. For every column that we are using silica per column, but for HPLC you need chiral column. And these are in like in chemical industry or that the in research also so we have that the very different kind of column like the column name is IA column, IB, the series of IA and sometimes the ADH, ODH. These are the name of chiral column. From the chiral column that you can separate by there is no we call them as a there's no mention of that this compound will be separate in that particular particular column that you should try in different column with different percentage. From that percentage that you will separate and first you have to check. Huh? It's not audible, guys. I think it should be audible because my internet is now it's audible or not because my internet is also now good, but I don't know if you are using that Ethernet that cable, but still it's not. Others, it's okay or not? Okay. Yeah, now it's okay or not? I mean, you just check. If it is not, then definitely I will reconnect again. Audible? Okay. Someone else is joining? No. Okay. These are the from column that we can separate only. Okay. That we can't say that any particular compound that will be separated in a particular column. That we have to be checked. Then only will report in a, that the different journal that this compound will be separated on that column only. From that only there is no such that specific things that we can say from that column only that you can separate that we call them any compound that any chiral compound like this compound whatever that the compound we are synthesizing in this molecule we can say but we have to try in different column from that column only when when you will separate then only that you can say that whether your compound will be separated or not. These are the mechanism, the little thing that you will know. But when you will synthesize any kinds of that chiral compound, the most important thing is to get that the much more enhanced selectivity. Generally, the greater than 90% enhanced selectivity will be that the good enhanced selectivity people think in that the research area. Greater than 90%. That if you got that the less than 90%, then your compound is not that much valuable for the application in organic synthesis. Okay. Then in the next question, you seen that we have decalane system, the alpha beta unsaturated ketones. When what will happen? When we will use that the sodium liquid ammonia, guys, what will happen? And what will be the product we will expect? I mean, trans will get major. Why? Trans will get major. Why not cis? Suppose that we are using the hydrogen like that, the hydrogen palladium in charcoal, then you will get that the trans or cis as a major product. The instead of sodium and the liquid ammonia. In that case, we will get cis because the addition of hydrogen that will be from that the same phases only. That's why we always get that cis one. Okay. Yeah, these are the other things for that. But in this case, we will get that the trans one majorly. It's like the exclusively will get as a that the 99% or is to 1% will get as a exclusive. This is only why that when the proton transfer will be happen in this case you just see in this case the proton transfer will happen from that proton transfer that will be to the we call them as the orthogonal, we call them as the 90-degree to our carbonyl group, that the carbonyl enolizable group that you see the guiding principle that's appear to be that the protonation of that the interactions are whatever that our intermediate anion in this case you see that's whatever the anion that will form that has to be that the perpendicular, we call them orthogonal because if it is that the orthogonal then you will get less steric hindrance. Because of that's only we call them as orthogonal. So that's our the enol double bond. First you just see that's the whatever that ketone will be there, that enol double bond and whatever your hydrogen that is the incoming hydrogen that will be to their are the orthogonal to each other. That's why we'll get always that the trans product as a major product. But in these cases, that as we are using sodium liquid ammonia, but in these cases only that you can reduce that double bond. Why not that you are our that keto group who won't be reduced to their corresponding that alcohol? Why only that keto group who will reduce? Why not that keto is sorry? Why only that the alkene will be reduced? Why not that keto group? Anyone? Guys, am I audible? Audible, okay. Yeah. If you are not saying, then I think that I am not audible. No. Okay. In this case, that it is not mentioned, but in the next slides I will show you. Okay. That's why in which cases that you see in this cases that we have that the alpha beta unsaturated ketone with that the different chiral center we have that in this the starting metal we have two different chiral center. See, and this molecule is a, that we call them as diastereomere selective molecule, and this molecule as we got as a single dia, as a single diastereomer. This molecule we got, and in the first condition we have lithium as compared to that sodium. That in this case we are using lithium and liquid ammonia. The solvent we are using diethyl ether, and we are not using any protic solvent. That we are using ammonium chloride. But in another cases that we are using liquid ammonia and ethanol. And what will be that the product you will expect? And why? That's if you got that the different kind of product, that why you will get that the different product as compared to the others. First, you just predict that the in first cases we will get that the which product, or in second cases that we will get that the which kind of product you will expect. Can you think that the only alkene will be only alkene if it is not alpha beta unsaturated ketone, that only alkene that will be reduced by that the sodium liquid ammonia solution? If it is only alkene that it is possible to reduce only alkene. So that's why whether it is possible that you are saying that the only alkene will be possible, that in this you see the our in the structure we have also an alkene also is there, that exoalkene also is there. You think that alkene will be reduced by Bose reduction? Yeah, yeah. generally alkene group will not be reduced that in presence of Bose reduction. Only alkene group. If it is only if it is if that alkene that is conjugated to that any kind of electron that we call it the withdrawing group, in that cases that it will be reduced. Particularly like in that cases we have the alpha beta unsaturated ketone. That's why it will be reduced. Then you just predict that the which product will get in that both cases. In the first cases, what will happen? In the second cases, what will happen? Which will become? Okay, we'll see. Yeah, these are the product we'll get. That in the first cases, because we don't have protonation, so that's a protic solvent. That's why we'll get the here the reaction will stop at that's that the keto stage. But when we have the protic solvent, in that cases, further reaction will be happen, and we'll get our final product. This is the condition you should need. That's why protic solvent, that is the most important things in Bosch reduction to reduce from keto to their corresponding alcohol. If you don't have any protein solvent, then you can't reduce your keto to their corresponding alcohol, because for that you need a proton from that carbanion to their corresponding, we call them as the alcohol formation. And stereoselectively, that's you will get that the trans product. You see that in this trans product, but after that, how you will get this OH1, I will show you. Okay, first you will show no that when you will yeah, that first your reaction will be in that the lithium, that the metal and liquid ammonia diethyl, then ammonium chloride. Then what does it mean that when you will quench the reaction, then you will give that the ammonium chloride. Okay. Yeah, proton it will be after to form that the keto. Okay, that's keto. Whatever that the inalizable that anion will be there, that will after that proton and it will form their corresponding keto. Yeah, I will show the mechanism. You will see first mechanism. Tell you. Yeah, actually different kind of that we call them alpha beta unsaturated ketone. Yeah, it will depend upon that the different condition. That if you have protic solvent or if you don't have any protic solvent, then you will get your corresponding ketone. Ketone. In the first cases that you will get ketone. That the without the protic solvent we will get ketone, but with protic solvent we got the corresponding alcohol. These, these are the that we call them as a reaction condition dependent product you will get. You see that what will happen? So there's everything. Yeah, what will happen first? It will that donate the electron and it will attack to our the alpha beta unsaturated ketones and you will get a radical anion. Okay. After that, it will after that proton whatever that the carbanion it will be for, but it will carbon for. But when you have that's proton that ethanol sir, then it will after that proton and you will get your corresponding that further reduction will be happen. But if you don't have any proton sir, then whatever your that inolate that it won't convert to your keto. Okay, because your that negative charge that will be more stable in your oxygen, it is not stable in your carbon, so that's why it can reduce again further. For this, when you will quench the reaction, that you will give the ammonium chloride, then it will take proton from that and it will convert to their corresponding that keto. But if you have any proton source, then it will convert to their keto first, then further reduction will be happen. And from that reduction, you will get your corresponding alcohol products. Okay, guys? Why? Yes? Yes, okay, na? Okay. Huh. And that whatever the stereochemistry in that the last cases, that why we got from that the below position the attack. This is only we got that always we got the thermodynamically favorable product. That's why everything it should be in trans. First you just check with ring junction. From that ring junctions only that your attack will be happen. When that you have a bicyclic compound, in that the bicyclic compound, the whatever your ring junction, that ring junction is your, we call them as less sterically hindered. From that junction only, that's your proton or that any kind of nucleophile that will be attacked. That's why in that case you will always get thermodynamically favorable product. But selectively how you will convert that the alpha beta unsaturated ketone to their corresponding ketone or their corresponding alcohol. These are the two different conditions. Okay, and this is our the next questions. That we have bicyclic compound, but still we have, okay, very good. Ah, that we have alpha beta unsaturated ketone also in this care, but we have that the cis bicyclic compound. Do you know that in bicyclic compound when we have that the five member and five member ring, in that cases that's whether your cis junction is much stable or your trans junction is much stable. The stability of cis is more stable. Cis or trans. In five member ring, then yes, am I audible? Okay, guys. Yes, this is more stable. That's when you have that the less member ring like five member or four member ring. In that cases, the cis is more stable. But when you have five and six member, in that cases, particularly depending upon your different substitute on your five and six member ring, that it will different. That whether your five and six member will be stable. But in six member your junction will be more stable. But in five like in that the five and six cases, this is the most important cases when you have five and six both the ring junction. In this cases, depending upon your substitutor, then whether your five cis and trans junction will be stable, it will differ. And if you want to know that we call them more about that one, then you just see that the Cleiden books, maybe that you know about Cleiden book. In that Cleiden books, that for bicyclic type of compound, that is six members, 6 5 and 6, we call it 6 4. If it is not possible that the 5 8, that 6 4 and whatever their stability, and why that cis is more stable as compared to their the trans, and why they're the trans transfer, that whether it is possible to exist there, that we call them a transform or not. Suppose that suppose that we just predicate transfer, but whether that compound will be more stable in your room temperature or not, and that we call them an energy also, that if this kind of, if you expect a trans compound with six and sorry, five and four ring junction, that's means that type of compound is very much unstable compound. That energy is very high. That's why in room temperature it will break. That kind of structure it won't be possible in room temperature. Maybe you will get in that the very less temperature, it will be stable. But in room temperature, that energy is very high. That's why for five and four ring, for we call them a trans junction, it will be very unstable compound. Ah, if we call them, want to know more about that the bicyclic compound, then you can refer the Cleiden books. But particularly, what will happen in dival, in this reaction we are using dival H. Maybe you know about the dival H. Yeah, what is the full form of that the dival H? Guys, diiso, yeah, diisobutyl aluminum hydrate. But in this case we are using that the 1.1 equivalent from that the diisopropyl. Sorry, that the dival H. Yeah, what will be that the product will have. And you see that the this reaction conditions also. That's we are using hexane solvent, that the N-hexane we are using, and the reaction is that in minus 78 degrees Celsius. That's why you should know at least that how the dival AC is much more reactive in room temperature. That's why we have to perform the reaction in minus 78 degrees Celsius. Generally, that to synthesize dival H in the laboratory, it will be very difficult. That's why people they are using that commercially available that dival H. And most of the people that most of the chemical industry they have stored that dival H in a toluene solvent or in that hexane solvent. In argon atmosphere, they have stored that the dival H as a solution. It's not that they have keep that the dival H as a reagent, that the particularly as a that the reagent they have used as a in different molar concentration solution. They have synthesized their dival H, and people are used that the different concentration of dival H from the different sources of that chemical company they have supplied, and people are most of now in whole over the world they have used that the commercially available divalent. They have not synthesized because these are very reactive one. If you are not careful when you will synthesize, maybe there is chances of blast or that the any kind of hazardous thing will be happen in your lab. So be careful when you will synthesize that any kind of that divalent reagent in a lab. Okay, but you will expect, sorry, yeah, which product you will expect that what will happen in this case? Yes, secondary alcohol, that our keto, sorry, whatever our alkene will be reduced or not? Oh, will get particularly that the allylic alcohol will get. You are saying that the allylic alcohol will get. Okay, na? Yeah, but whatever that the allylic alcohol will get, whether that's allylic alcohol it will comes from that the above position or that the below position. What will be that the OH group, the stereochemistry of OH group? Can you predict that the stereochemistry of OH? OH or dash? Yeah, am I audible now? Same plane. That is the OH and our that ring junction, the whatever. Yeah, these are in same plane. Whatever your why is this so? That's can you tell? Mhm. Do you know that what is that the structure generally in what are the phases in that the bicyclic compound that when it's that the 5 and 5 member ring junction is 6 junction, then we have two different kind of that phases. Like I'll show you how it will be like in we have two phases that we have two five memory. This one is a five memory and this one is a five memory, and we have that the two cis hydrogen. This is a phase and this is also a phase. This one is phases and this one. Suppose that we have two different hydrogen, and these are the two five memory. This one is a phases, this one, and this one is a different phase. From which phases your attack will be happen, that it will be different. That which phases of your that bicyclic compound that will be less crowding, that phases your reaction will be happen. But in this particularly cases that we have two different, we call them as a convex and that the concave phases. You see, this is that one phases that will be towards our hydrogen, that whatever that the both hydrogen cis hydrogen will be there. In another phases that will be present in that the both the ring junction like open book. So whatever I'll show you, this is that the open book like that, so that the both hydrogen will be there and both ring will be there. Okay, these are the two phases, and from which phases our the data will be happen, that the from less steric index like that the both hydrogen, that we have two hydrogen is that the above and that the two ring junction that will be in that the below. So that's why your attack, whatever your hydrate donor, that will be from that the above phase. That we call them as from to get the our final product. That how we'll get our final product. First, we should fix that the our ring junction. Suppose that your ring junction that will be present in that wedge position, then your attack will be from that the wedge position because our wedge that is plane is that of less sterically hindered as compared to the our other phases. Why? Only because in above in other phases that we have two cyclopentyl group, but in another phases we have only two hydrogen. That's why our attack will be happen from that the hydrogen phases. That the whatever ring hydrogen junction from that phases only our attack will be happen. You see that in this case, whatever our hydrogen anion that will be attack to from that our ring junction faces only because that ring junction faces is much more less sterically hindered as compared to our other faces because in other faces we have two different cyclopentane that group. That's why it will cause a steric hindrance to them and will get exclusively that's this the trans alcohol to their corresponding our ring junction will get exclusively. Suppose that's your the ring junction is wedge position, then you will get your attack from that the wedge position only, and you will get your hydroxyl group in gas position. Okay, guys. Sorry. And now, can you expect that what will be the product in this cases? Yeah, this is a very simple question. I think. Why? Oh, maybe then you would know that hydrate will be for. Yeah. Yeah, this kind of that sodium borohydrate and sodium that the trichloride in that hexahydrate. These are particularly that's when you have that the for example keto and aldehyde that to reduce that sorry that to reduce more less electrophilic ketone that we can reduce by using that sodium borohydrate and sodium trichloride. How it will form? That it will form. Why this is only because that it will form a hydrated ion. With that the hydrated one, you should see the mechanism. First, that's we have aldehyde and ketone, but among them, which one is much more reactive? Our aldehyde will be that the much more reactive as compared to our ketone. That's why first it will react with our whatever Lewis acid will be there, that the sodium trichloride, that it will activate our keto groups, that sorry, aldehyde group, and whatever that the water the reaction that will be present in that hexahydrates, that it will attack and it will form a hydrated formation. As you will see, through hydrolysis, we will get a hydrated. That's why that it will mark our the aldehyde group to their corresponding hydrated one, the hydrated formation that the in presence of sodium trichloride, and then only our keto group will be reduced that in presence sodium borohydrate and will get our corresponding. And again, that's from hydrated one that it will bring to their corresponding when you will do workup. Before workup, you won't get your corresponding from that hydrate to your corresponding aldehyde. If you don't do workup, if you do workup, then only you will get your from hydrate to their from hydrated form to their corresponding aldehyde form. This is the most important thing. If you don't do workup, then your compound will stay as a we call them as the dihydrate form. That's all. Because this dihydrate we call them as a which type of functional group is this one? Can you tell? Yeah, yeah. Call them as the hemiacetal, acetal like that. Okay. Yeah. Huh. You just ignore. Yeah, this is our the next question. You just see. Yeah, this question is a very tough question. Very tough question. Okay. That's for some book also. That's a very tough question. Yeah. Can you predict that the which that the what kind of reaction will be happening? Yes. No. Okay. Anyone or others? Whatever Venkata, that's you are not audible. That's clearly for me. That is not clearly audible. Yeah, yeah. You say that what will happen? Yeah, but that the which one will be that clip and you will think that will get algae. You think that will get algae? No, we won't get algae. But you see that we have. Okay, but that one will clip. That's the that very good answer. But which side one will be clip? Because we have two different that the oxygen and that both oxygen will be different. You see which one? Right sides. Why? Is there any reason that okay? Generally, what will happen that in dival age also that it won't reduce that alkyl. Okay, the dival age that it can it can't reduce that the that any triple bond, but it can reduce that if you have any we call it propyl alcohol, that kind of group or that any kinds of that any propyl alcohol is a that we call it exceptional group uh, cases that in that cases particularly that it is possible to reduce our alkane, the influence of divalent in that and there is another cases that I forgot but uh, right now that I can't recall. Huh? But there is another cases also that in that cases that if you have triple bond and alpha 2, then if there is particular group that I forgot that one. If that group is there, then only your alkyne group will reduce to their corresponding alkene. Okay. But generally, that alkyne are very that we call them as unreactive towards that our divalent reduction. But in this particular cases, what will happen? That whatever we have that acetyl group we have, you see, when we have that the divalase that it will attack to the it will bind to we call them as coordinate to our the both oxygen. It is possible, but which oxygen will be much more feasible because of that the steric index. You just see when we have that the in the first cases that it will causes a steric index with that or that the aliphatic chain with containing our alkyne fat. But in another cases, in that another oxygen, we don't have any steric hindrance. That's why second one is much more favorable as compared to our first one intermediates. That's why because of the that's intermediate only, that's our oxygen lone pair that will donate it and it will form a that we call it oxycarbonium cation. You just see this oxycarbonium cation will be formed. No, sorry, and the ring will be open. And from that ring only, that we have hydride ion in that divalase. And that hydride ion will attack to our oxycarbanion group and will get our corresponding that ether. You see, this is a ether group will get. Okay, this ether group will get and our oxygen, the oxygen and carbon bond will be cleaved. In that the whole process will get uh, our oxygen and carbon group will be cleaved, it will cleave and we will get our less sterically hindered oxygen the oxygen carbon bond will be break and we will get your corresponding alcohol after workup only that you will get that when you will do workup then you will get your oxygen and aluminum bond will be break and you will get your corresponding OH. This is only because of that the steric index that if there is no steric index between that both oxygen sorry that both that the oxygen near to the oxygen then both will be possible, but in this particular cases this group is much more sterically hindered. That's why selectively only we will get that the carbon oxygen bond will be break from that the less sterically hindered group, but we won't get any aldehyde but we'll get that the alcohol group. See that's how we'll get that the alcohol group. This is the mechanism that first that's when it will form a that the coordinate to our oxygen then that the another oxygen lone pair that it will form a we call it oxocarbonium cation intermediate, and from that only that we have hydride ion in aluminum that we call the divalent. In already in that the coordinate toward that we call them as another oxygen. And after that only that we have a hydride transfer will be happen and we will get our corresponding alcohol product. Alcohol and ether. This is a primary alcohol and ether also will get. Okay, that's any question? That why? Yes. No. First, you just see these are more stable. That's I think. But to bind that the first it will bind na the whatever our dival is first it will bind. But from which side that it will bind that first you will check. If there is a stirring hindrance from in that the other person, then it is not possible to bind in another phases. Na you just see that in that both oxygen that the less sterically hindered oxygen will be bind with our the divalent. Then only we will get a that the primary alcohol. Yeah, that's the thing. But in these cases that we are not getting directly alcohol. From the ketone to we won't get that alcohol. You just see in these cases only particularly the carbon oxygen bond will be break. That's when there is a chances of that you will get from ketone to that the we call them as the primary and secondary alcohol. In that particular cases that you will get. Yeah, yeah. My simple question to everyone, that's when we have that any carbonyl group, that's the carbonyl group, and you and I'm giving any that the nucleophile, that the any kind of nucleophile, then it will react to the carbonyl group. Then the angle of attack of that the nucleophile to that the carbonyl carbon. What is that the angle of attack? Please unmute, guys. Okay. Sorry. Please mute. Okay. Yeah. The general general angle of attack when that the any kind of nucleophile to that the carbonyl group, the angle of attack is what? The angle of attack of that the nucleophile to that the carbonyl carbon group. Yeah? The angle of attack that we have a particular angle. Angle of attack at which degree that it will attack to our the carbonyl group. 90 degree. Anyone others? Yeah, there is a name also for that degree. Maybe that you know about that the 107 degree Celsius. Sorry, that 107 degree that 22 minutes. That Burji-Dunich angle. Maybe you know. Yeah, Burji-Dunich. Burzi Dunich Dunij. That angle of attack. So that the any kind of the carbonyl group. So that any kind of nucleophile that will attack at that the 122 sorry 107 degrees Celsius 107 degree 22 minutes that it will attack to our carbonyl group. You know or that you don't know that what is Burji-Dunich angle? Oh, okay. Then I will explain. Okay. Yeah. Generally, what will happen that the if there is a carbonyl group, uh, there is a carbonyl group, then the most actually when the attack will happen from that generally that it has to be happen from that the 90 degrees. So what we are saying is that from 90 degree, that will we call them as a reasonable answer. But from 90 degrees, it will get that the less steric hindrance. That's why it has to be comes from that we call them as the 90 degree. But in reality, yeah, these are not the case. Why? When you see first that whatever our carbonyl group, this carbonyl group, this is generally what will happen in carbonyl group that it will attack to our pi star. That's whatever the pi bond of that the carbon and oxygen will be present. In that case, the their pi star whatever nucleophile we have that it will react to our that the carbonyl pi star group and the we call them as the orbital overlap of carbonyl 5 star group is like that. You can see this is that the carbon and oxygen, and generally it will react at the carbon position. And whatever that we have that the nucleophile and they are homo, because homo is a phase of that the nucleophile. The whatever the carbanion you will get or that any hydrogen ion, this is one phase. When it will comes to that the 90 degree, what will happen? Then it will causes both that we call them as the to that the carbon center that it will causes a bonding interaction, but it will also causes that the anti-bonding interaction with that the oxygen 5 star orbital. That's why the 90-degree attack of nucleophile it won't be possible because that it will causes both bonding and simultaneously also it will causes an anti-bonding in because of the interactions. Because of that both bonding and that the anti-bonding interaction, that's why whatever that the angle of attack that will shift to a we call them as a such angle that it has to be in a, that 107 degree Celsius. If it is comes from that the 107 degree Celsius, sorry, degree, then it won't causes it will causes minimum that we call them as a minimum the antibonding interaction with our oxygen one, and also minimum steric hindrance with that the both are. That's the also most that the we call it. Because that if you attack from we call them as the 130 and 140 degree Celsius. Sorry, 130 degree and that the 140 degree. In that cases, what will happen? The steric hindrance will be more, but here we call them as anti-bending interaction will be very less. That it won't be there any kind of anti-bonding interaction with oxygen one. Suppose that if your angle of attack is 140 and 150 degrees Celsius, but in that cases you will get a severe we call it a severe steric hindrance with your both that the substituent that is present in carbon that both are group. That's why to minimize both that the steric hindrance and also there the antibonding interaction there is an angle, and that angle is 107 degree degree 22 minutes. That's angle we call them as a Boursy-Dounis that a trajectory. Okay, this is that the particular angle of that attack. In that attack our no, we call them as the steric hindrance to that the both R group will be very less, and also there is no anti-bonding interaction with our that the oxygen that 5 star orbital. It will only causes that the nucleophile whatever the nucleophile it will only causes the bonding interaction with our the carbonyl the carbon group. If it is comes from 107, but if it is comes from that 90 degree Celsius 90 degree, in that case it will causes both one. That's why it will slightly move to that the 107 degree. Oh, and in that cases that it will causes less steric hindrance with our substitution of the carbonyl group, and also there is no antibonding interaction with oxygen, and that trajectory we call them as a Boursy-Dounis as a trajectory, and that one is the 107 degree and 22 minutes also. Okay, I am not mentioned, but that one is also 22 minutes. And that if you want the more detail that you can see in we can call them as Cleidian books also. The molecular orbital, how the molecular orbital of any carbonic group that will react with any kind of that any kind of nucleophile. Suppose that you have a carbonyl group. Suppose you have any carbonyl group that will reacts with that so carbonyl group, and also that in carbonyl group in your alpha position you have any halogen group. In that cases also there how their homo and lumo will be there, and how it will react, and who only particularly. Suppose I will show you. Okay, go ahead, guys. Let me give it the answer now. Wait, guys, I'll show you something. Yeah, it is audible. Sorry, is it visible now? In clearness, you see that if you have a particularly that the carbonyl group in that case, and also that the halogen group that the in alpha position we have halogen group. Then in that particular cases that why the Angelov, sorry, when if you have any E2, sorry, that the nucleophile, then it will attack to the carbonyl group or to that our that the carbon halogen group. Okay. It will attach to the carbonyl or to our carbon halogen group. You will see from that the molecular orbital only that you can explain. And why that it will only attack to our that the carbon, the chlorine bond or that why it will attack to our carbonyl group. That is from that the your homo-lumo interactions only that you can see. Okay, these are not the our topic discussion, but from that for every kind of homo-lumo interaction, then your angle of attack or like that your angle of we call them as the stereochemistry and how their homo and lumo will react to get that any kind of products. For every kind of reaction, there is an we call them interaction between homo and lumo. For every nucleophile, there is there is a homo orbital, and for any electrophile, for every electrophile, there is a that the LUMO orbital. And when that the HOMO and LUMO will react, then you will get a bond formation. From that bond formation only, that your reaction will be happening. Okay. Yes, yes. Speak loudly. I'm okay. Speak again. No, not always. That's it. In that particular carbonyl groups, in that cases, if you have that in that particular cases only that you will get your angle of attack is that 107. Suppose that in SN2 reaction, then whether your angle of attack is what? In SN2 reaction. In a, backside attacking because in SN2 reaction, your 5 star orbital, sorry, 5 star, your sigma star orbital of your carbon and whatever you have the X group, your halogen or the leaving group, in that cases, your sigma star orbital that is present to that whatever your bond will be there, carbon X bond group, if it is a sigma bond, then their sigma star will present that we call them as a 180 degrees Celsius. That's why your angle of nucleophile attack will to it takes place from that the 180 degree. It will defend it which that position it will attack. It will always defend. Oh, okay, then I will show you that. But in this cases, that why will get that only particularly that the 76% of that the fast product that we call them axial attack. Why and also we got that the 24% of that equatorial attack. Why? That can you explain? Yeah, this is the results that if you have that the we call them as lithium aluminum hydrate. It's not stable. The stability is very, suppose that if you have a that instead of lithium aluminum hydrate, that if you have a that we call them as any bulky like I'm forget that some bulky that hydrate reagent. In that cases, you will get as a major product as a your we call them as the axial alcohol group. That if you have use that any we call them as a bulky hydrate reagent, that the hydrate donor reagent. In that cases, particularly you will get that your axial alcohol as a major product. Selectively, maybe you will get as a more than 99% also. In that case, it is not that your the axial and your equatorial will be stable. In this particular cases, you will get your equatorial as a major product, but you will get also some axial. Axial as a 24%. But if you use that much more bulkier the hydrate reagent, like that the iso sec butyl that something is there that aluminum hydrate, in that cases you will get your axial alcohol will be much more stable. Sorry, much more not stable, much more sorry. The as a major product you will get. Sometime also exclusively you will get the as a more than 99% also. But the reason behind is that from that the charge confirmation also you can say. Okay. Any questions? Do you have any questions? Okay, if you have any question, then you can ask. No problem. Yeah, that's for every carbonyl group. that if you have any that the axial attack and that the equatorial attack, what will happen? For every kind of axial attack, then it will you see for the hydrogen. Suppose that we have only cyclohexanol group. Then in that case, that we have different kind of the hydrogen. You just see that I am numbering the 2, 3, 4, 5, 6. For every that's carbon, that we have that equatorial and axial hydrogen also. But in these cases, only I am showing the we call them as the axial hydrogen. I am not showing any that the equatorial hydrogen. I am only showing that our axial hydrogen. Then when that if any kind of nucleophile that will attach to the carbonyl group, then if it comes from axial, then it will what will happen? Then it will causes a stirring hindrance with our axial, that we call them as H3 and H5. You see this one H3 and H5, that it will causes a stirring hindrance in that the both cases. If it comes from axial, that's mean in that cases we call them as the that's our S3 and S5 hydrogen, that will cause a steric, much more steric hindrance with our axial hydrogen. But when it will comes from that the equatorial one, in that cases it's cause a torsional state. Torsional strain and steric hindrance, you know that what is the difference between? That you know that what is that the difference between torsional strain and you know that which one is that the much more that when there is a interaction between that the high axial interaction and that the axial we call them as equatorial interaction. In these cases, then that which one is that the much more energy and which one is that the less energy? Yeah, axial and equatorial is that the less energy. Okay. uh, Most of the time that's our attack will be happens from that the equatorial also. Then only we'll get what we'll get, that we'll get our major product as a which we call them as the axial alcohol. And this is product we call them as the kinetically controlled product. But what will happen when your nucleophile is very small? Okay, when your nucleophile is very small, in that particularly cases, that what will happen? Then your attack will be happen from that the axial attack to get more most that we call it much more stable. We call it thermodynamically stable alcohol product. When your nucleophile is very less, so we call it as a very less bulky. But when your nucleophile is that the much more bulkier nucleophile, in that particular cases what will happen, then you will get that your angle of attack will comes from that equatorial, because that's your nucleophile that has to be comes from that the equatorial to minimize the interaction with different kind of hydrogen that will be present in your that cyclohexanol. That's why if you have bulky that's in the nucleophile, in that particular cases your attack will be happens from equatorial attack. And when you have that the less bulky, that the very particularly for that the lithium aluminum hydride or sodium borohydride or lithium borohydride, in that particular cases your most of the major product that will happen from that the axial attack, and you will get your we call it the most stable thermodynamically, that we call them as equatorial alcohol you will get. But when you have any uh, bulkier nucleophile, in that particular cases you will get less stable product, but still you will get that the major product as a your axial attack. This is only because that's when you have bulkier group of that the nucleophile, because in that cases it won't only donate that the hydrate one, because as we have lithium aluminum hydrate from that aluminum hydrate bond that will break, and that will donate, that will attack to our carbon. It not that lithium aluminum hydrate that first it will transfer hydrate air, then only it will react. It not like that. It is like that what happened? Uh, our hydrogen that will bind to our aluminum already, and that hydrate ion will be transferred. That means that whatever our lithium aluminum hydrate, that whole things will attack to our carbonyl group. But when you have that the instead of a lithium aluminum hydrate source, suppose that you have that the lithium aluminum that we call them as secondary say that the isobutyl and hydrate ion. In that particular cases that you have only one hydrate, but you have three that the secondary we call them as secondary isobutyl group. In that particular cases, what will happen because of that three particular secondary isobutyl group, that your angle of attack will happen from that the equatorial position. Because of that only. That's why in that particular cases you will get your equatorial attack. To simply remember that how it will attack. Generally, that the bulkier nucleophile that will attack from equatorial one to minimize the we call it as minimize the interaction with that the axial hydrogen, that is H2 and H6, and that the less bulky nucleophile that will always attach from our axial one. And in some cases there is a border between that the both axial and we call them as equatorial attack will be happen. And these are some particular cases will be there. In this case you have to be remember that for which kind of nucleophile that you will get that the which kind of particular, because there is a we call them as a medium kind of nucleophile also will be there. Okay na, in this case in that particular cases that you will get both product also, both product will be possible. Like as a 50 to 50% it is possible. So to get selectively that the one kind of alcohol that we use that the much more bulkier hydrate reagent to get selectively axial product. Or if you use that a very less like that called the very less bulky that hydrogen reagent, in that cases you will get selectively your that the equatorial alcohol as a major product because they thermodynamically alcohol. Yeah, these are the general things. It is not only for that the hydrogen ion. This is only also for our that any kind of nucleophile that it will attack to carbonyl group. That any kind of nucleophilic addition to that the carbonyl group. This is that the fundamental thing that from which side attack will be happen from axial or equatorial one. And if you have that the if you want to know that the more detail about that the carbonyl attack, that you can refer the books. I forgot. I will tell you. It's not Carathar. One more book is there. I forgot. For that master student. No, the Glidden is for that the bachelor student. This is standard book for bachelor student. There is that another books also there. I forgot. Glidden, Zuifel. Maybe you know about Zuifel books. Zuifel. The Zuifel book is the best. Okay, for this type of that the angle of attack. The Zuifel books that you can follow. Leader is good, but if you want to know more about that the reaction or some the reaction also, then you can follow that Zuifel books. The Zuifel books also for different kind of problem also that you can follow Zuifel. Carathar also very good, but in Carathar, for Carathar to read the Carathar, you should know that the basic your basic has to be very strong. Okay, guys. Then what will happen in the next question? Maybe in this question that we already discussed that how we will convert that this one, because by using that the particular sodium borohydride and selenium trichloride, then what will happen that in this particular case what we did generally thus we have aldehyde, ester and keto group, but we only reduce our the keto group to their corresponding OH group. That will only possible when we have sodium borohydride and that is sodium tetrachlorides, because that sodium tetrachloride that will form a hydrate one, and from the hydrate one that it will mark our aldehyde and our keto group will be there, and it will reduce by our sodium borohydride and we will get our corresponding the alcohol group will get. Yeah, these things or this concept we already discussed also in the maybe in the previous one, but this is another example. Even that in presence of ester group also, that we can that reduce particularly only keto group to their corresponding alcohol, and to keep that remaining our the aldehyde and ester group. It is possible that if you have the keto, ester, and that aldehyde, we selectively that reduce our keto to our corresponding secondary alcohol that in presence of sodium borohydride and selenium trichloride. But if you use the lithium aluminum hydride and the sodium borohydride, then you will get a mixture of product. You will get mixture of product. You will get. Okay, and this is my that the next question. You just see this is based on that The stereochemistry, how you will decide the stereochemistry? First, you just check. In this case, what will happen? That which product you will get? How you will confirm that? Yeah, there is a Cram's rule. From that Cram's rule also that you can decide that whether your angle of attack will be from which one. But this is a rule. But from how you will we call it explain that that the which from which side your angle of attack will be much more feasible. How you will explain? Yeah, there is a model. The from that model only we can explain. There is a model you can see. Yeah, whatever it will come down and up. And that's one. Yeah, how you will explain? That's why how why that's always could come to the down either down or wedge. That it not matter. But how you will explain? That's what there is a model. The Cram's rule is there. Cram's is a rule. Huh? Whatever that the Cram's rule is a rule. It's not a concept. But there is a model. From that model, we can explain. Do you know Felkin and model? Felkin and model. Felkin and model. Felkin and model. You don't know? You are that the master student or what? All that the master student they definitely know about the Cram's rule and Felkin and model. Felkin and model is that the model. From that only that we can explain from which side your angle of attack will be there. Sorry, from which side your angle of the nucleophile will be attacked. Pelkin and model that you can check in different books you will get from Newman projection of any kind of we call them as a chiral aldehyde. This is a chiral aldehyde. People now they are joining. I don't know why. Because it's already that 8:46, but people still want to join. Who is that guy? Okay. For any kind of that the chiral aldehyde, and if you have any kind of nucleophile to our carbonyl group, in that particular cases there is one rule from a we call them a Cram's rule. From Cram's rule that will always predicts our product, that the which kind of products will get. Okay, that the which kind of product will get, that you can whether that you will get cis or trans, whatever that is from Cram's rule you will get. But to explain that the stereochemistry, there is and the model we call them as a Felkin and model. From that Felkin and model only we can explain. But it is very difficult to explain in that the online classes. But I will try because generally Felkin and model to explain in online classes it is very difficult. But I will try. How will they? Let's see. I will show with some slides that will say. In these cases, what will happen? That the major product will get that are hided from that the above position, and as a major product will get from that the below position. Okay. For any kind of that the carbonyl, that the chiral carbonyl group, that if it is not particularly that chiral aldehyde or that for any kind of that the alpha in your alpha position, if there is a chiral center will be there, like the position, and the guys for that only that we have to be decide that from which side your angle of attack will be, sorry, from which side your nucleophile will be attacked in a particular case. That's we have that in particular that the chiral center that we have that the three different kind of that groups. You see that the large and small. Yeah, this is for that the general one. Okay, this is that the general one. First we have to draw that the Newman projection. Newman projection of that the both carbon, that the carbonyl carbon and our chiral center carbon. This one in carbonyl carbon that we have only two group. That's why we should keep as them as the 180 degrees Celsius. You see this that we can put as a carbonyl and our R group. And according to that, whatever the circle is be there, the circle is nothing but our that the next carbon. And always that you should know that whatever our largest group that will be present, that is 90 degree 2 hours. Whatever our group will be there, the carbonyl group that will present to our the 90 degree. Why no 90 degree? Because that largest group that will be from that we call them as the, to minimize that the steric hindrance, that if it comes from the, if your large group that will be present in 90 degree, then you will get very less amount of that the steric hindrance. But suppose that if you put that's in that the instead of our small group, whatever that the S will be there, if you put that the L group, then you will get much more steric hindrance with our R group, that we call them a carbonyl R group. That's why your largest group, that whatever R group, sorry, L group, that will be present, that is 92 degree to our carbonyl group. And your the medium and that the small group that will be present according to that. First, you should fix your largest group, and according to them, that your medium and small group that will be present in your Newman projection. And how to draw Newman projection, that you just check that how we will draw. That's our Newman projection from that the any kind of, that if you have any two, that we call them as the chiral center, that the chiral molecule, that the we call them as diastereomer, for that how to draw the Newman projection, that you can check the different books also. This is that is easy concept. And that we call it the, without showing that the any model, that it will very difficult to explain that how it will be present in that. But generally, for your convenience, I will explain that this is our carbonyl group. Suppose that it's our carbonyl group, and we have a carbon group. And carbon group, that the our largest group, that you should always be placed in a, that is in our plane only. First, we just fix our largest group that will be in plane. In this particular session, see that our L group and our keto and R group that will be in a plane, and our medium and the large group that will either in OH or dash, that will differ. But you should always put your, if you have a, suppose you have a question, in that particular question, that is your largest group that will be in that the, we call them as in OH position, then you can convert to that that the, first you just keep your largest group in a plane, then only you will decide that how it will be, what is your conformation for your keto, that the Newman conformation. Okay, and this is that there is variety of the, we call it as the infinity number of Newman we call them as the conformation would be possible, but the most we call them as a more stable, more stable conformation for this particular keto and that the, we call them as a chiral center. These are the only two most conformations, that the most stable conformation. This both one, and it will always depend upon that your we call them as R group also. Suppose that your R group is the hydrogen, then it will depend that whether your first will be much more stable, or your second conformer will be much more stable. It will depend. First, you have to be draw that's your uh, that chiral aldehyde or ketone in a Newman projection for that the more stable conformer. Then what will happen? First, we will do for this same question, for same question that we have, that are two different kind of. First, you just see our phenyl group is that the most more bulkier group. Okay, this one is that the much more bulkier group, and that's why first we should put our phenyl group that is perpendicular to our the carbonyl group. This was the our carbonyl group, and this is our phenyl group. That is always in that both cases our much more bulkier group that will be present, so they are perpendicular to our carbonyl group, and our methyl and hydrogen that will be present. But first we will check from which side of attack that will be much more favorable. There is four type of attack will be there. First one this one, second one this one, third one this one, fourth one this one. Okay, then among them the first one is the much more hindered one. Generally, I told you that for any kind of carbonyl group, the angle of attack is what? That 120 degrees Celsius, 107 degree. In this particular cases also, that we have from the carbonyl to that we have 107. You just see whatever the arrow will be there. This the angle of arrow and our carbonyl, that is nearly that's equal to 107. That the 107. For all that angle of attack, the first angle of attack is much more. We call them as just sterically less hindered as compared to other ones. For second one, that is close to our phenyl group. For the third one, that is close to our the phenyl group also. And fourth one, that is close to our methyl group. But our first one, that is close to our hydrogen group. That is less sterically hindered. That's why our attack will be happen from that side. Okay, from that side, your attack will be happen. See, and and whatever your keto bonds, that that will convert to our the corresponding hydroxy group. We call them as the corresponding alcohol group. And after that, then you just draw from the Newman projection to that our the that the wedge just position that you just transfer. How you will transfer? That you just fix that the two bond. That whatever pH and H bond first you just fix, and you will draw that both methyl and OH group that will be in if it is either in wedge or that in below position. That you can fix that both that in one line, that either methyl or ethyl, OH and H, and hydrogen or pH. Or you can also that you can rotate also, that you can rotate the 60-degree again, and you just take the for best thing that first what you will do, that you just check that we call them as the largest group, that the largest both of that are like pH and our that ethyl group, that in this particular case the ethyl group, that we keep them as a, like we call them as the call them as the you just do that rotation in a such a way that your both largest group of that both carbon that will be present in 180 degrees Celsius. Then only that you just fix that the other substitution whether they are present in same sites or that the other sites. Suppose that in this particular cases I will draw. Do you know that the how to convert from it's already off. Guys, wait. Suppose I will that whatever ethyl group that will be present for this carbon, this is ethyl, this is hydrogen, this is OH. Suppose I want to that to rotate 120 degree, then what will happen? Then this ethyl group comes to here, then OH group comes to here, sorry, the hydrogen, then OH group comes to here. Okay, that instead of that we will get here what, that ethyl, in this case we will get hydrogen. Okay, in this case we will get OH. For that we will get that both our hydrogen, sorry, the ethyl and pH group in that the same plane. That's pH and our ethyl group that will be in that the plane. Then our methyl and OH group, that our methyl and OH in that particular case, then whatever methyl and H, because this H comes to that OH, the in that case methyl and hydrogen that will be in same side. You just check methyl and OH that will be same side, and our hydrogen and OH group, that this one will be the same sides. You understand or not? Otherwise I will draw. Guys, you will respond. You understand or not? Yeah. Otherwise I will draw. For everyone this is because to drawing the, because I don't have any that the pen stand or anything, because from laptop only I am teaching, that's it very difficult to draw, but I can draw that if you rotate 120 degrees Celsius, then you just fix here both that the longest carbon chain. After that you will decide that whether which group that will be present from that the same sides or that the other sides. That is the simple thing. If you still have any problem, then you can say in the next class, because we have already 8. It's always because today the time is, and that the next question also like same also, that we have carbonyl group and we have a chiral center. From that only your stereochemistry will be different. But the last questions that I have some interesting questions. And that the last question, what will happen? Hey, anyone can you say what will happen in the last cases? Can you see them? This kind of questions in that the any books or that the any the competitive exam that have you seen anyone? Huh? Slides is not visible. What happened? Yeah, actually, what happened? That when I convert to that the presentation mode, that when I am using any that the ledger point, then what will happen in that particular cases? Then maybe the slide is not visible for that some people I don't know. Okay, but in this cases, what will happen? Now it is visible, na? Okay. Okay, the answer is there. It's okay. Just to see the answer is there because in the slides I am already that detailed because I am not detailed. But first you will say in generally what will happen that if you are only that imine group, then it is not possible to reduce that imine group by the sodium borohydride reduction. But if you have that the iminium ion group, in that particular cases, that it is possible to reduce that the iminium ion group to the corresponding amine. The second, this is the iminium ion group, and that we are reduce that in present sodium borohydride to their corresponding that the we call them as a amine. This is particular we call them as a tertiary amine. This nitrogen is nothing but the tertiary amine. That's why in our starting material we have the iminium ion. But why that we only get that the 92% from that the below attack, and why that we only get that the 8% as a above attack? Because the stereochemistry is there, na? The stereochemistry is there, then why we'll get that call them as the 92% from the below position attack? Because when your hydrate will come from below position, then your methyl has to be in we call them as the above position. Why? Do you know that for any kind of alkene and that the imine, for any kind of alkene and imine or that the alpha beta unsaturated ketone, the conformation for any kind of that the six member ring, then then what is that the conformation? Trans is not like the trans like that we can say. This is not trans. You just see that if there is a trans between 1 and 2, then that trans is more stable. If there is a substitution between 1 and 3, not for any that is cyclohexanon, then we can say from that our chair conformation. For any kind of cyclohexanon or that the any kind of that the halogen group or that any because the living group that will be present in cyclohexane ring. But for any kind of alkene or that alpha beta unsaturated ketone, then yes. But in these cases, we got that the cis one na for the if there is a the I had agree. Okay. Do you know that the what is that the conformer that we call it as a conformer for that the alkene or that the any kind of alkene or that imine group? Yes, the conformer. Maybe you half chair conformation you have seen. Have you seen that any kind of half chair conformation like this? I'll show you. That you should read some books. You just see. Yeah, yeah. This is for any kind of alkene group to decide from that which side your angle of attack will be happen. This is the conformation. That is much more conformal, much more stable conformer we have. From that only that you will decide from which side your angle of attack will be there. From below or above. But in this particular case, from below side your angle of attack will be happen. Why? The structure I have drawn, but why the angle of attack will be from below side, why not from that the above side? Then I have drawn that the everything, but you should tell that's why it's from that below side, why not from that the above side? You just see in that particular cases that whatever the structure is there, it's not that we call them as the thermodynamically favorable product because in these cases methyl group that will be present in equatorial and our that the CH2OH group that will be present in that the axial group. Then that's why these are not that the more thermodynamically, because you are saying that it's not trans. If your both adjacent compound that will be present trans, then these are the called them as the most stable product. But if 1 and 3 position, that will be in cis position, that 1 and 3 substituted, then that kind of the cyclohexane ring, these are more stable. That's cis one for 1 3 substituted. For 1 4, the trans will be the same. For 1 2 1 4, the trans will be more stable product. But for 1 3, the cis is most stable product. Why? This is only because of both substituent. That if it is, suppose that's your CH2OH group, that will comes to our, we call them as the I'm not audible. Okay, okay. I'll check. I'll check. Now I'm audible? Yes or no? Okay. Okay. In this particular cases, what will happen? Yeah. Actually, there is two faces. That's from bottom and that the above faces. Okay. But our bottom faces will be, attack will be much more favorable. Why? Because when our bottom faces bottom face attack will be happen, then it will directly convert to our corresponding chair conformation. But when it will attacks from that the above position, then first it will convert to a we call them as a twist board conformation. That will be that conformation. From that conformation to again it will convert to their corresponding chair conformation. It will take a two step to convert from that the twist board. First it will convert to twist board, then again that will convert to their corresponding chair. But when it will attack from that the below position, then it will convert directly to their the chair conformation. That's why our angle of attack that will be comes from that the below position only, and we will get major product as a below position. This is a one step, that if you attack from this one on that carbon, then our nitrogen that will come, and whatever this carbon that will goes above, and whatever this carbon that will, this is below and this is above, and this carbon that will go above, and this carbon will come below this one, water methyl group, and we'll get directly a chair conformation. But if your attack of angle will be from that above position, then you will get a, we call them as a twist board conformation. Because of that, twist board conformation is not stable as compared to our chair conformation. That's why our angle of attack will be comes from, we call them as the axial. In this particular case, say that the axial attack will be happen from that the below position. So that is the only reason, that if you put, sorry, that okay. Do you know that the how that the okay, half chair conformation, or how that how, from that half chair conformation to how it will directly convert to that the cyclohexane, or that we call chair conformation, or that the we call the twist board conformation. That if if your attack comes from the above position, then it will convert it to their corresponding half chair conformation. Half chair conformation. You just see when it will attack, then this one will come down. Then you will get a half chair conformation. But when your attack will become, that means your carbon will go upward. Your carbon will goes upward. Then you will get a chair conformation. Yet that the angle of attack. Sorry, from that which side your attack will be happen. That it will depend on here that the which intermediate, which conformer will be formed, that your twist board or your cyclohexane, so that is chair conformation. If it is formed chair conformation, then that's why your chair conformation is much more stable, and you will get as a major product. These are the only reason. Any doubt still, or that's maybe you have doubt, but okay, okay. Because what will happen actually, yeah, to explain this kind of, I have to do. Okay, in next class that I will draw that the half chair conformation also, and also that the chair conformation I will draw in chem draw, and I will show you again. Okay. Yeah. Yeah. Thank you. Thank you. Okay, you can leave. Good night.